Ma'am, you mean like omega, big O, and theta?
Omega, theta, and big O.
Yeah. So, and what are these? What does big O means? What does omega notation means? And what is this theta notation means?
And like the capital O or the big O, like it measures the highest, like the longest amount of time the algorithm can take to complete the code, like to run the code.
Yeah, right. And what about the other two?
Omega is like the optimal or the best solution, like which uses the least amount of time.
Yeah. What about theta?
Theta is the average time.
Yes. Yeah. So we discussed like a brief between what are these things, and we have seen few algorithms and how do we estimate the time complexity of those. And yeah, I discussed a bit about space complexity as well. Right? So in this class, I'll I'll show you some few more examples. How do we estimate the complexity? And we can take, like by taking those, we can consider those to be kind of already, like you can say the formula kind of thing. So once you are encountering such type of course, then you know what is the time complexity. Like you will be knowing as you and when you practice, but after certain time you will be also have like it will be by just by taking by seeing the code, at least you can see if the for loop is running in this way, what would be the specific time complexity of that particular chunk of code, right? So and also I'll give you some explanation about the, is my screen visible?
Yes, ma'am.
Yes, ma'am.
I'll give you explanation about the definition of the all three type of notations, the big O, the omega, as well as the theta notation. So to start with, if you see, so if we take this chunk of code, what would be its time complexity just by looking into it? What would be this for loop? Simple: I equal to 0, I less than n, and I plus plus. How many times the statement would be executing? Can anyone of you tell? Yes.
N times.
N number of times.
Yeah, so it will be of the order of n, right? Similarly, what about this 4? I equal to n, then I greater than equal to 0, I minus minus.
N number of times.
N number of times, right? And what about this one? It is having I starting from 1 less than equal to n and I plus 2, right? So what would be the time complexity? It is incrementing or order of 2, right? It is every time it is like taking I plus 2, right? So what would be the time complexity?
N by 2, ma'am.
N by 2. So what would be the order? It will be again n, because we are taking the polynomial part, right? Similarly, in this case, so this is the case I think we have discussed last class also. What would be the time complexity of for loop inside for loop? And this condition
N
is that,
square.
yeah, it is of n cross n, so n square. Right now, similar to that, if you see this particular code where we have I equal to 0, I less than n, I plus plus, j equal to 0, j less than I. Okay, it's not going till I, it is not going till n, and we are taking j plus plus. So what would be this one? Any guesses?
Can you repeat the question once again?
This one, for this particular code, I equal to 0, I less than n, I plus plus, j equal to 0, j less than I, and j plus plus. how many times this statement would be executed. So this will be executed in a little bit different way, since here we are not taking n till n, it should not go. So what would be the case is, like, let's see. So this one, what we are doing is, here I equal to 0, we'll see how many times this statement is executing. So I equal to 0, j equal to 0, it won't be executed, right? If you take I equal to 1, then it will be, it will take, okay, j less than I. So for j less than I, this is, it will be executed for 1, and so when it comes to j equal to 1, it won't be executed, okay, because it's not less than I. So only one time it will be executed. Similarly, if you take the next case, I plus plus, that is 2, so this 2 will be executed, and when this equates, it won't be executed. So it will be executed for 2 times, and 3, so 3 times it would be executed, and so on and so forth. If you take till I is reaching till n, here j is not reaching till n. So what we will take is, for n time, I equal to n, it will be executed for n times. So till how many times it will be executed if you take this in both the conditions. So you can say this many times we are having this, the statement is getting executed. So this we know, if we add it up, it will come as 1 plus 2 plus 3 plus n. So we know n into n plus 1 by 2. So we can take n square plus 1 by 2, and we are keeping the fastest growing term. So that's why the order also is n square. So same, it is same as the previous, but not in the same way what we have estimated, because this one is not going till n, because it is, we are getting the order of n just by taking the number of statement counts. How we are getting it is, it's not exactly behaving in the previous way, where we have both I less than n and j less than n, right? Okay, so every time you are given a problem, you have to check what condition this loops are saying, right? Is this clear, this one?
Yes, ma'am.
Yeah. Now we'll see another case. So here what is happening is, we are taking a variable p equal to 0, then we are taking for I equal to 1, p less than n, I plus plus. Okay, this is I plus plus, and the statement is p equal to p plus I. So what we will get here? So here what we are taking for I equal to, let's start p equal to 0, p was 0, then we have taken I equal to 1. So I equal to, for I equal to 1, it will be what? 0 plus 1, that is 1. For I equal to 2, it will be what? This p plus I, right? So p plus I is 1 plus 2, 3. For 3, it will be 1 plus 2 plus 3, right? For 4, it will be 1 plus 2 plus 3 plus 4. Every time increment of p plus I, right? Similarly, what will happen is, here if you see, here I is not, again, we are not taking I less than n. Here we are taking p less than equal to n, right? So it won't be executed. I is not getting executed till n times. I is definitely getting executed less than n time, and we are taking it as let's suppose we are taking it as k times. Okay, and for, if you are taking k, then it will be again 1 plus 2 plus 3 plus until k time, right? So this, what we will do is, what is our condition? So till this, it will run p less than equal to n. So what is the stopping criterion? We can call it as p greater than equal to n, right? And instead of this p, we can add here this format as k plus k into k plus 1 divided by 2, that is greater than 1. So it will be approximating to k square. So k square greater than n. That's why k is equal to, we can almost approximate this to be it is order of root n. Okay, here we are not going till n, we are going one value which is at least less than n, right? Because I is not less than n here. Is this clear?
Ma'am, I have a doubt.
Yeah.
Ma'am, why we have taken p greater than and assume why we have, because in for loop it is p less than equal to.
So this one, till this it should run. So what is the stopping criterion? We can say it will end when p is greater than equal to n, right? That is the
Yes.
case taken here. Okay.
Oh,
Yeah. So similarly, there is another case. where we can see this as for I equal to 1, I less than n, and I equal to I cross 2 and the statement. So what we will say is what we are taking for I equal to 1, it will be running for, so for I, so first we are taking I equal to 1, so in this case it will be running as I 1 into 2, then it will be of, if you take I equal to 2, it will be I cross 2, that's why 2 cross 2. It will then for third, it will be, when I equal to 3, it will be this cross 2, right? Whatever is there in I, that is cross 2, that is to the 3. And here, what we are taking is, so since it is again the multiplication of I cross 2, so we are considering it is running till like k times. So that's why if we reach till k, so it will be of 2 to the power k. The same if you are incrementing and all, and we are reaching till k, you are getting the value is 2 to the power k. So this condition, till this condition, it is running, right? And the stopping criterion here, that's why we are taking if so I is greater than equal to n. If we take this as our condition, what is the stopping criterion? We can consider it as I greater than equal to n. So I instead, in place of I, we can put how many iterations we have run. So that is 2 to the k. So 2 to the k greater than equal to n, and k is of log of n base 2. Okay. So when we have such type of equations for I equal to 1, I is less than equal to n, I equal to I cross 2, then we can say we are having the log order, the time complexity in the order of log n base 2. Is it clear?
So the order is log to n.
Log n base 2. Just log n order. Okay. So log n is less than n, order of n. We'll see what the order, what is this order. Okay. So similarly, if you take I equal to n, it is starting from n, then I greater than equal to 1, it is checking. Then what we are doing is we are dividing it by 2. So for this case also, what we will see is in the statement. So what we will see is at start I was n, then so it is getting divided by n by 2. Okay. Then next case it will be divided by n by 2 square, and so on. It will go till n by 2 to the power k. Okay. So this is our condition till this we can check. So how many times it will be executed? Obviously it won't be executed n times because of this condition. So it will be executed, let's suppose k times. So we can consider this as this is our stopping criterion. So we are assuming I is less than n, it will be terminated. So for this condition, we are taking as n divided by 2 to the k less than 1. Okay. So in this case, so when we are taking n divided by 2 to k less than 1, so n and we are approximating n as 2 to a k. So again, k we are getting as log of n base 2. So for both the conditions, we are taking, if we are taking I to I cross 2 or I divided by 2, we are having this time complexity in the order of log n. Okay. So these are various cases what we have seen. When, yes, can you please mute yourself if you don't have anything? Yeah. Okay. So these are the cases what we have discussed with. Sorry. When we are encountering this type of thing, so once you practice, it will come anyway. So you know for certain cases, if you are encountering such type cases, what is the order? If it is the square root of, or it is the simply the log n, or if it is n square or nq or polynomial or factorial type. So with practice, you will know. But there are few things which is like after doing for a certain amount of time, trying it out, you can anyway take it as a formula also. Right. So these are some base conditions for the things which we have discussed now. Similarly, if you take this case where I equal to 0, I cross I less than n, and I plus plus, here what we are doing is, here we are just taking this condition I cross I less than n. So this, if this is the case, then what would be the terminating criteria? I cross I greater than equal to n if it is less than n. So I square we can approximate as n. then I will be of the order of root n, right? So for this condition, you can take it as it will be order of root n. Similarly, for this condition, what we are taking, f of I equal to 0, I less than n, I plus plus, j equal to 0, j less than n, j plus plus. So these are two separate loops. That's why what would be the time complexity for two, this type of loop? Yes,
N plus n.
n plus n, that is n. Okay. So yeah, these are the things which there are a few more things also. You also can try it out on your own so that you will understand a bit more about it. Then we will see some of the definitions of this asymptotic notations. To start with, we'll see what is this big O notations at formal definition. So what definition wise what it says is that is f of n equal to order of g of n or og of n. So just hang on with this concept. So it is taking about if you are taking any kind of function of which we want to find out the order, right? So this equal to O g of n, only there is some positive constant c and n0 such that the function f of n is greater than equal to 0 and less than equal to c g of n. So c is the constant for all n greater than n0. Now what does that mean? So what we do is, let's suppose we are taking a function f of n that is 2n plus 3. Okay, so we need to find out the order in such a way that this condition is holding true for us for all n, for all values of n that is greater than equal to n0. That is another constant. So here constant c and n0 are two constants here. So if this condition is holding true, then we are calling this as f of n equal to O g of n. Okay, or we are finding out the big O notation for this. Now, so and this is the notation which gives you starting from order of 1, then you can take log n which is greater than that, root n which is greater than log n which is greater than this, and log n square. So these are the things till it goes till n factorial. Okay, right? So this is basically order, and you can have many more orders. The dots are in between, and that here also you can have if you there is this n log n is there already. So you can, this is basically the order. So what we have to see is, given this function, how do we go for this finding out the big O notation? So for this condition should be holding true. So what we will do now, if we are taking 2n plus 3, so we will find some value of in the right hand side, some value of this cg of n in terms of cg of n. C is our constant such that this condition is holding true. So let's suppose we have taken here as 10n for all n greater than equal to 1. Okay, here n0 is 1 here. So for all n greater than equal to 1, this condition is holding true, because if you put 1 here, so here if you put 1, what we will get? 5 is less than equal to 10, right? That means what this 10n, this 10n is your cgn now. C being this 10 and n is your g of n. Okay, so this way, what? So this is one condition what we have checked. Now you can similarly you can try for 9 and you can try for the 7, 8, 6 and okay. So in this way, you what we are checking here is there are many possibilities of finding out this the order of n in the right hand side, right, in terms of cgn. So where exactly do we find the exact or the order of, if we are calling about this function, where exactly we are finding out the exact order of n? So what we will do is, what we are doing here is, so we have taken as less than 10n. So now we have taken, let's suppose 7n. So here what we are taking is, here we are taking 2n plus 3 less than equal to 2n plus 3n. So that means we are getting this 5n. So if you take for all n greater than equal to 1, if you take this 5n, it is giving you, it is still having the condition, it is holding this for 5n also it is holding true. This condition is holding true. So this has now become our, I can say, the boundary value of it. Okay. Is it clear so far? We are just trying to find out the boundary value. So now we know here that f of n is O of n, right? As per our formal definition. So if I add one more thing to it, like I can say instead of 5n, I can add it, I can take 2n plus 3 is less than equal to 2n square plus 3n square. Still for this condition is holding true if you take n equal to 1. For that also this condition is for all greater than n greater than equal to 1. For this also this condition will hold true, right? So that means what? Similarly, you can go for further higher orders also, and still this condition is remaining valid for this criteria, right? So that means what? You can take f of n equal to O of n, f of n equal to O of n square, or like the order exponential also you can take. But you cannot take f of n that is order of log n, which is falling in the other side of it, like n lesser value than lesser time complexity than this n. That means what we are talking about is, here is this f of n is the exact boundary position, we call the average bound, but beyond this the upper bound case also is holding true for this big O notation. Okay, is this clear so far?
Ma'am, and that's when I have a doubt, like why we have not taken O of log n.
So this log n, if you put here, if you find the value, this won't be, this will, the value will not be valid for this particular condition. Okay, for all.
Okay.
Yeah, that's what I don't have, I have not found out the exact the actual value which we get, but it won't be since this. So if you see the this order in which it is increasing, starting from the order of 1, okay, the constant, and going towards log n, root n, and the n log n, and n square, n cube, 2 to the power n, right? The exponential term, then n factorial. So in this way, if you find it out, it won't be holding true for this particular case. So it is holding true for all the other cases, but what is best to be found out is only the average bound. That is the best thing to be found out. But other conditions are still holding true. Similarly, if you see the asymptotic notation for this omega g of n, so for that also what we are doing is we are just doing the reverse. So f of n equal to omega g of n if there is a positive constant c and n0 such that f of n is greater than equal to cg of n, right? It is just the reverse for all n is greater than equal to n0. So same equation we are taking. What we are taking is 2n plus 3 greater than equal to some value of n. Okay. So what is that? Now we can take, I can take just one n, right? For all n greater than equal to 1. So for this condition also it will, this equation is holding true. Okay. Similarly, as I have checked for, if you again put the values for higher orders, it won't be working. But for the lower orders, that is below the n, that will be holding true. If you take the log n, now this condition will be holding true for all n greater than equal to 1. So what has happened is, here we have found out f of n is equal to omega of n. That is the average bound, or we can say the boundary value, which is which boundary value is for which boundary value we are getting the exact exact time complexity. Okay, that is for order of n, right? Or here we are calling it as omega n if we are talking about only n, okay, that can go in this direction also. That's why we are taking all the lower bound case for um, the omega n, right? Similarly, if you take this condition for the theta n condition, which is the average bound case, so here only exactly one value should be valid for our case. Okay, so here what we are taking, same function we are taking. So the definition says, so if and only there should be a positive constant c1, c2 and n0 such that fn should be greater than equal to c1 g of n and less than equal to c2 g of n for all n greater than equal to 0. So by taking both the left side and right side condition, we will be able to find out fn f of n only for order of n case. Okay, it is not for any other case. That means what, for average case condition we have only one value, and if asked which is the best notation to be put is the average one, only the average one. If you are not able to find the average one, you can go for the upper bound or the upper bound or the lower bound case. Okay, so this way we represent mathematically the the asymptotic notations, be it big O or omega or theta notations. So for theta notation, we have only one exact value. For big O notations, we have the upper bound case is valid, but it's better to find out what is the boundary value. Okay. Similarly, for the omega notation, so we all the lower bound cases are valid, but it's better if you find out the boundary value again. Okay. Is this clear so far?
Yes, ma'am.
Okay, so that is it for today. I'll give you a quick quiz. You can open your Moodle, and it's a small quiz. You can solve it in, I think, 10 minutes time. Is it visible?
No, ma'am.
No,
Yes, it's
it's
open.
visible, right? Yeah, okay. So once you're done, you can leave the meeting.